right, question.
And it seems to be going. Yeah, okay.
Where should I sit?
Wherever you like, I guess. There's a chair right there. If you want to improvise with that, you might want to roll that back somewhere we have more space. Yeah. Sorry, this is my first time teaching in this classroom.
I thought this is an actual. No, I don't think so.
Oh, okay. There you go. Okay.
It's just someone's cool jacket.
Okay. So welcome to Math219. Clark Bray, nice to meet y'all. Welcome to the course. Y'all have already heard me, if you watched the recording per the email that I sent. So y'all have already heard me talk about all this stuff here. I'm not going to go through that all again, but I do want to hit just for the appropriate to how important the point is. I want to remind you the big learning goal for the class is this is a class about ideas and reasoning. That this is fundamentally what the course is about, right? This is not a matter of memorizing formulas and rehearsing algorithms and stuff like that. So try to always look for any homework exercise that you do, any reading that you do in the book or in my lecture notes, or when you're trading ideas with friends, right? The focus should always be on how do these ideas work, and not what's the answer to number 17. That kind of thing. So anyway, again, I went on at great length in the recording, so I won't repeat all of that stuff. Before we get into math, I also want to discard. I'm not sure what happened there. I also want to point out in the course resources section. So y'all have seen me talk about this at least a little bit. But after I made that recording, I then remembered I had forgotten to include the help room. This semester we do have a multivariable calculus help room. It's a very cool resource. A lot of good that you can get out of it. You click right there, it takes you to the schedule. And in particular, here you go, multivariable calculus. You can see Math219 is included, and here's the location and hours right there. So it's a great resource, no appointment necessary. Just show up and start asking questions. So enjoy. All right. Let me pause real quick, see if anyone has any questions. Everybody okay? Okay, so we'll do a little bit of math here. Let's see here. Okay. Well, anyway, so before we get into the book content, I want to entertain a natural question to think about at the start of this course, and that is, why are we here, right? Why are you taking a course in multivariable calculus? Why is it important? To the question of why you're taking it, I like to point out that very possibly it's because your major requires it, right? Natural next question. Why does your major require for you to take multivariable calculus? By the way, if you're here just out of intellectual curiosity, that's awesome. Anyway, but if your major requires it, why do they require it? And it's because it's such a big deal. I'm going to try to persuade you with some examples and such as to why it's important. But I'm going to start with single variable calculus, because I think you're probably already sold on the idea that single variable calculus is important. It's a big deal. It's very useful. After all, derivatives are how we understand how things change. The world is full of things changing. Everything's changing right all the time. So derivatives are how we understand that. It's a obviously hugely important concept, and you've seen bazillions of examples of that in Calc 1 classes. Integrals. Why are integrals important? Well, in general, this is how you compute what I like to call accumulating quantities. Now, what I mean by an accumulating quantity, anything where the whole is the sum of the parts. So, for example, if I have a lump of Play-Doh, right, and if I want to know how much mass is in this lump of Play-Doh, if I were to break it into two chunks and take the mass of the one chunk and the mass of the other chunk and add them up, that would give me the mass of the original, right? So the whole is the sum of the parts. If you think about applications you've seen in the past in your Calc 2 classes or what have you, every time you've computed something with an integral, It has been on the basis of this property, among other things, that the whole is the sum of the parts. So accumulating quantities, and it turns out there's just bazillions of accumulating quantities that can be understood in this way. I'm going to move this over here so I don't trip on it. Okay, so why isn't single variable calculus good enough? Right? I mean, it's clearly super important. And ultimately the point is this: single variable happens in one dimension, really. If you think about it, functions of a single variable are functions that are defined on a one-dimensional domain. When you do an integral or when you take a derivative, right, the domain is just the real number line. We don't live in a one-dimensional world. We live in a three-dimensional world. Now, that said, I will recognize, right, that yes, there are some circumstances where single variable calculus can already apply in a three-dimensional setting. So, for example, everybody's seen the example where you have a tank, right? Some sort of a three-dimensional tank. It's buried under the ground, and you got to pump all the sludge out of the tank, right? And the sludge is more dense at the bottom, and it's less dense at the top because that's how gravity works, right? And so, how much work does it take to pump all that sludge out of the tank, right? Conveniently, the density of the sludge happens to only depend on altitude. It only depends on height. So even though there's sludge distributed across an entire three-dimensional volume, in some sense there's really only a one-dimensional dependence. Right? So yes, single variable calculus in a case like that is good enough for solving a three-dimensional problem. But frankly, that's a little peculiar. Right? How often do we expect to just get lucky and only one variable matters? Right? So, for example, you walk out into the garden out there, grab a rock. You ask, what's the density of the rock? Well, it changes. There's some igneous over here, and there's some sedimentary over here, and probably an iron deposit a little over there. It's going to vary in all directions. It's not just, you didn't get lucky with this one where it only depends on one variable. Density will depend on all three variables. Right? So most of the time, single variable calculus isn't really going to cut it. So let me show you some, I'm going to call it easy first examples where we truly need a multivariable approach in some sense, and single variable is just not going to do. So for example, let's suppose that I'm here, and I'm moving with a certain velocity, like so. And suppose I'm interested in temperature, and now in the real world, temperature depends on all three variables. Right? It depends on longitude and latitude. Just look at the Weather Channel anytime, right? It's a wildly varying with respect to all variables function. Even altitude, right? So here at the surface of the Earth, the temperature is a little chilly today, right? But if you go up 20,000 feet, it's even chillier. So temperature depends on all the variables. That's just the way of the world. And so if I am moving with that velocity, and if I'm interested in how fast is temperature changing as I experience it, in other words, as I move, the temperature, I'm going further and further over this way, where the temperature is changing as I go that way. How fast is temperature changing? And single variable calculus is not going to cut it for a question like this, because there's three variables. They're all changing. X, Y, and Z are all changing. And we're going to have to figure out how to deal with that, and how to figure out how to incorporate all of the different variables. You buy it? Okay. So let's see here. This next one, and we've kind of already in some sense talked through it. Imagine this is a lump of Play-Doh, right, or whatever. And if the density depends, again, on all three variables, which, well, again, of course, there's a certain amount of density, but maybe it's extra dense up in this corner up there, and maybe also down in this corner down there. Well, density depends on all the variables. I can't just multiply volume times density, because density is not constant. I also can't just slice this up like we would in a Calc 2 class, because on any given slice, for example, on, let's say this, I didn't mean to do that. I wanted the pencil, sorry. On this slice right here. Right? The density down here is not the same as the density up there. So again, I can't even use a single variable integral for the same reasons. Density is not constant on the slices. Depends on all three variables. We're going to have to figure out a way to deal with this, right? Our current understanding of how to use integrals to turn big problems into small problems isn't, the ensuing small problems aren't small enough. We still don't know how to solve it. Okay. All right. How are we doing? Everybody happy? Okay, so multivariable calculus is going to help us address both of these problems. In fact, I'm going to call these easy starter examples because they're sort of obviously rip-offs of single variable calculus questions. They're also kind of, not that scary looking, right? We're going to have to figure out some techniques, but it doesn't look that bad. So now, what I'm going to also show you then is some application-specific examples. And these are probably a little bit scarier looking, a little bit more sophisticated and intimidating looking. Starting with an example from, I'm going to say economics, and what I mean by this is that there are economic models that are expressed by an equation relating various variables. I kind of made this one up. I just wrote some stuff down because the specifics of the model don't really matter here, and I don't know any economics, so I just wrote down some stuff. But if you were to take an econ class and look at an economic model, it's going to involve some variables, and it's going to be an equation that describes how they all have to relate to each other. So that being said, suppose I have control over L, K, Q, and I. By control, I mean either that I literally can choose to change them as I see fit, or maybe I understand exactly how they're going to change because of, well, for whatever reason, like maybe interest rates, maybe I just know factually that interest rates are going to be going up or whatever. Knowing how those change, can I, using this model, anticipate how price is going to change? Well, I mean, the sort of the Calc 1 point of view on this would be to solve for P, right? But you can't solve for P, right? Look at P here. P shows up outside of the exponential and also inside of the exponential, and you just cannot analytically solve for P in that situation. So what we have here is a multivariable version of something that you might have seen already, a single variable, kind of pseudo single variable version of the implicit function theorem and the implicit differentiation. So when there's 5 variables, that does change things, but nevertheless there is a multivariable version, and we can use multivariable calculus to answer this question. Even though we can't solve for P itself, we're going to be able to understand how P changes without actually solving for it. Okay. What do you think? Any questions? Yeah.
What does NB there mean?
Oh, I'm sorry. This NB right here, that's, I'm going to confess, I don't really remember with certainty what that stands for. It's a Latin phrase.
Nota bene.
Is that right? Nota bene? Okay.
Yeah.
So, and it's Latin, is that right? Yeah. So it means, by the way, heads up, here's an important point to be aware of, something to that effect. Yeah. Good question. Anybody else? Okay, so I like to point out while we're here, there is a common misconception centered on kind of this point right here, that the world is three-dimensional, and if our case for why we need more than a single variable of calculus is that, well, hey, we live in a three-dimensional world, the subtext, the seemingly suggested idea is that, well, we need enough multivariable to be able to deal with 3 dimensions, and thus that we need to be able to deal with functions of at least 3 variables. But is 3 dimensions enough? Now, a lot of people would say, well, it better be. I mean, the 4th dimension's a scary concept. Doesn't that have something to do with, like, Isn't that science fiction? Is that really a thing? The fourth dimension? Is it like black holes and time travel and stuff like that? I mean, it seems very sort of far out to talk about more than more than 3 dimensions. But let me just point out, dimensions don't need to be location coordinates. They just don't. Right? You look at this example right here. We have 5 variables. We are doing math in 5 dimensions here. So, of course, if we're going to be able to apply multivariable calculus to the, let's face it, not particularly sci-fi field of economics, it's very real. Economics is a very real world, right? We're going to need to be able to do calculus in definitely more than 3 dimensions, as needed, just depending on how many variables there actually are. So don't fall for this business about 3 dimensions is good enough. Now here's the good news. 3 dimensions is a kind of a imposed upon us limitation on us personally. Right? I am a 3-dimensional critter. I do not have the ability to think in 4 dimensions. I have tried really hard. I don't think it's possible. Right? I've never heard of anyone reliably, believably, actually being able to visualize literally in 4 or more dimensions. So I'm not going to expect that of y'all. Right? So what we're going to be doing is we are going to be studying things in 3 dimensions. We'll be drawing 3-dimensional pictures. And then a good thing to keep in mind is that even though you can't actually visualize 5, ask yourself, how would the algebra that we've written down in a 3-dimensional context, should that change if I had 5 variables instead of 3? And is there any reason that we need to tie this down to only 3? And things like that. So anyway, something to keep in mind. Everybody happy with that? Okay, moving along. Physics and engineering makes lots and lots and lots of use of multivariable calculus. That was probably something you already assumed and understood. Here are some examples. Now, these are from E&M, electricity and magnetism. And this equation right here, for example, first question to ask is, what does that mean? What is this thing on the left, where there's kind of 3 integral symbols right next to each other? What on earth is that? That's something we're going to have to figure out and make sense out of. Right? Likewise, this thing on the left, now there's only 2 integral symbols, but I'm a little scared of this. There's a differential that appears to also be a vector. That's pretty creepy looking, right? So what does that mean? That's something we're going to have to make sense out of and figure out. Right? So one of our goals is to be able to understand certain specific multivariable calculus objects and constructions. Okay. Then another sort of further question is, how do we actually make sense out of these statements? Like, how do I know this statement is true? It's one thing to understand what the object on the left is and understand what the object on the right is. How do I know these are equal? Oh, it's really not immediately clear. There's good reasons for it, but how do we know? Right? So that's going to be one of the big ideas that we're going to be talking about. This is, well, let me not give it away. But anyway, there are big ideas behind where that comes from. That's going to be something that we're going to be interested in as well. And then furthermore, once you understand where this equation comes from, very reasonable next question, how does that help me understand electric fields? For reference, this capital E here is something called an electric field. So how does this mysterious statement circled in blue, what does that tell me about electric fields? And the neat reality is that understanding this multivariable calculus will help you generate points of view on how to think about electric fields, how to think about magnetic fields, and stuff, and other related objects that are inside of this these equations. The math will help you understand the physics, not just computationally, but also intuitively, how to think about it. So, tremendous amounts of stuff. So again, it's not just a matter of just computing stuff. It's that we can have a better understanding of how physics and engineering work on an intuitive level because of ideas of multivariable calculus. Okay. All right, now here's one. We're actually not going to spend much time talking about this one, but it's not really our goal here. This is not a preview of the course. This is me trying to persuade you that multivariable calculus is important. And this one comes from, I'm going to say, chemistry in a sense. If you're a chemistry major or if you're interested in chemistry, you're going to need to understand molecular bonds. That's how molecules hold together. Kind of a big deal, right? How does that work? Well, it turns out that molecular bonds come from understanding the behavior of electrons. Okay, how do we understand the behavior of electrons? Well, it turns out electrons obey what's called Schrodinger's equation. So the theory goes anyway. So this is one of the fundamental equations of quantum mechanics. If you are a chem major or whatever, if you ever take a physical chemistry class, you will see Schrodinger's equation, at least a little bit. And in order to make sense out of Schrodinger's equation, again, for the purpose of understanding electrons and therefore bonds and therefore how chemistry can happen, right? What you will need, among other things, is to understand this deal right here. What is that? Turns out it's a big deal, and it's multivariable calculus. This is a natural object of multivariable calculus. And we're going to talk about that in this course as well. Not the quantum mechanics, not the Schrodinger's equation, but this object here we are going to talk about. So very important in just huge numbers of fields. It's not just that we're going to be taking obvious simple extensions of single variable problems, but we're going to be doing stuff that applies, you might say, all across campus, all the natural sciences and half of the social sciences. Big deal. The way I like to say it is that multivariable calculus is the calculus of the real world. Because, again, single variable is just too simple to describe the realities that we're actually faced with. Everybody good? You believe it? Okay. All right. Okay, so moving along, and I think I accidentally closed the window of what I need next. So let me just open up the next. Let's see here. It's going to be here. Discard. Normally I'll have this better organized. There we go. Okay, so off to the book. Now begins the actual material for the course. We're going to start with Chapter 1, of course. Everything in Chapter 1 pretty much is about vectors and ideas related to vectors. Y'all have seen vectors before in Math219 or 221, whatever linear algebra class you had. I think somewhere between some and all of the stuff in Chapter 1 is stuff that you have or should have seen previously or digested to some degree. So I don't feel that I can just skip the whole thing, right? But on the other hand, this is should be review. At least a lot of it will be review for, I think, most students, if not all students. Different amounts for different students. So anyway, I'm going to remind you, I do have to make some what I've called tough choices, right? I don't have enough contact time to be able to talk about 100% of the ideas and examples and applications and tips and tricks and little mathematical life hacks and all the little cool stuff that I want to be able to talk about. There's just not enough contact time. So I have to sort of pick and choose what I think are the most deserving of class time, and things that you either have seen before or that are just natural extensions of things you've seen before. It's a relatively low priority. So I'm going to go a little quickly through Chapter 1. That's just a heads up. Reminder, though, you have to fill in the blanks, right? So if I skip something in Section 1.6, for example, that you maybe don't really feel particularly comfortable with, then you're going to want to polish up on that on your own. Okay. Reminder, office hours. help room. Don't forget you're also invited to the other instructors' office hours. Right? So you've got a lot of different resources. I also encourage, by the way, to group up, form study groups, work with friends. If you have a question, don't forget about that easy resource. Just ask your friend. Okay. All right, but plenty of resources if you need any blanks filled in. Okay, I'm starting with 1.6 because the things I'm going to say about 1.6 are, frankly, all linear algebra. It's all stuff that really should have been covered in whatever linear algebra course you took. So I like to get 1.6 out of the way, and then we'll go on to things that may be a little bit less prerequisite-y. So starting with the triangle inequality. Now, again, you may have seen this, may not, I don't know. But it's a pretty easy one to talk about. The triangle inequality just says that if you look at a sum of two vectors and look at its magnitude, namely that distance right there. And then if you look at the individual vectors and look at their magnitudes, the total of the magnitudes, which of course is this distance plus that distance, in other words, that overall orange length, right? The triangle inequality just says that the blue is never more than the orange. Or as the way I like to think about it, it says that the shortest distance between 2 points is a straight line, which again I think geometrically really believable, right? Hopefully this is an easy pitch. Is everybody happy with that? Intuitively at least? If you want to see a proof of this, that would be done in a linear algebra class, but we don't need to concern ourselves with that in 219. Okay. All right, so useful here and there. Moving along. Now this next one I hope you've seen. It's about matrix multiplication. I'll say matrix vector multiplication. A lot of y'all you've definitely seen matrix vector multiplication in some form or another. For a lot of students, the preferred sort of favorite way to do this is what I'll call the dot product formula, where you take the rows one at a time of the matrix and just dot with the vector. And you just kind of dot, the vector you dot with one row at a time, and that gives you the coordinates of your product. That's handy when you're doing computations. We have computers for that these days, right? So the actual turning of the crank and the actual computing of the actual numbers, not really the big point, right? That's not what we need to understand. What's far more important is to understand how this operation, right? How does this algebraic concept relate to other algebraic concepts, operations, objects, whatever? And much better in that sense, I think, is the following. That a matrix vector product is a linear combination. Which I think is a little bit unexpected even, but specifically, it's a linear combination. You can see right there in that formula. That's literally a linear combination. More interesting, it's a linear combination of the columns of the original matrix. Well, that's pretty weird, right? It does not just leap off the page if you're thinking about it from a dot product point of view. If you're thinking about it from a dot product point of view, you're looking one coordinate at a time. Here, we're understanding matrix vector multiplication as a statement about vectors, not as a statement about coordinates. Different, right? Very different point of view. And then furthermore, not only is a linear combination of the columns specifically, but the coefficients in that linear combination are the coordinates of the original vector. So what I love about this point of view is that this connects ideas, right? And it turns out, and we're going to see an example in just a couple of minutes, it turns out that when you have a point of view that connects objects and ideas, that's just a much better, a more powerful tool for proving and for understanding and for exploring. And again, that's what we're here for. Okay, so I hope this is familiar. If this is something that you saw, but you, yeah, I don't like that one. I like the other one, and you kind of maybe blew it off. Make sure to digest this one thoroughly. I think this is a really important part of linear algebra. Okay. Actually, I don't like that. All righty. Linearity. You may have heard the term linear transformation at some point in the past. A linear transformation, that's just a big word. It just means a function that's linear. That's all it means, right? So what we really want to focus on here is what does linear mean, and linear means this property right here. So hopefully, presumably, you've seen this. Again, this is one of the fundamental concepts of linear algebra, the idea of a function being linear. There's different ways to think about this. My own preferred personal way of thinking about this is that, I'll say it crisply first, the function plays nice with linear combinations. What I mean by that is, notice if you look at how this is written, you can put the linear combination on the inside before you apply the function t, or you could put the linear combination kind of, if you will, on the outside after you've applied the linear function t, and you get the same thing either way. So apply the linear combination before the function, apply it after the function, doesn't make any difference. That's a pretty neat property. In some sense that it's like the function is transparent to linear combinations. As this moves back and forth, before, after, as you see fit. Very, very handy algebraically. We're going to see, again, examples coming up in a few minutes. So make sure you're crisp on this being the definition of linearity. If you want to prove something is linear, plug it in. Make sure this works. If this works, good. It's linear. Everybody happy? For whatever it's worth, there are equivalent alternative formulations, and if this were a linear algebra class, we'd talk about how to prove that this implies these and these imply that, etc. That's not what we're here for, but I want y'all to be aware, and I want y'all to be comfortable that these three different equivalent formulations are all, in fact, equivalent. Okay. All right, some examples. Dot product. Let me say it sloppily first. A lot of people would sloppily say dot products are linear. Now you might complain that dot product is not a function. A dot product is an operation. It's got to have two inputs. So what does it mean if I say that it's linear? And that is a valid complaint. And I was sloppy in my statement, but very often people do that just to be, crisp and succinct. So what precisely do I mean when I say linear in this case? We are talking about this function p. This function p that applies to a vector x. So what I want to do is look at this formula and see what happens to x in this formula. What happens to x in this formula is what p is. What happens to x in this formula is that it gets dotted with a. So when I say that p is linear, what I mean is the act of dotting with a fixed given constant vector a is linear. Now I'm going to leave this as an exercise for y'all to confirm on your own. I think this is a nice exercise. Again, if you want to prove something is linear, the way you prove something is linear is by making sure that it satisfies this property right here, right? And so all you have to do is take this formula for this function p and plug it into that property and just check and make sure that the left and the right side are always equal. Now let me clarify one thing. When I say I'm going to leave this as an exercise, I don't mean a homework exercise. You don't have to do it. You're not going to submit it. Although it does happen sometimes that things that I'll suggest in class as that'd be a nice exercise, sometimes they coincidentally happen to also show up on the homework. That's just a coincidence. So I don't want to say you'll never do it. But that said, when I make a suggested exercise, you don't have to do it. But I think it's a really good idea. I think it's a good bit of practice. So I hope you'll entertain the idea that you might actually write this down and work it out. It'd be good practice for the exams, for example. It has happened more than once with no intention on my part that when I was writing the exam, I came up with a question. I thought it seemed like a good question. I forgot that was a suggested exercise from class. That I don't do it on purpose, but it has happened. And I think the reason it happens is because when I say, hey, that's a good exercise, it's because it's something I think is interesting and important. And that's the exact formula that I'm looking for when I'm thinking up exam questions. So it's not that surprising. So something to think about, right? Try to have a system in place for making notes for suggested exercises, and take a few minutes at some point to come back and maybe you make a note, something like that on your notes as a reminder that you want to actually go through and confirm that. Okay. Okay, moving along. Let's see here. Cross products, also linear. And again, it's suitably interpreted. What do I mean when I say cross products linear? Well, what I mean is what happens to x, right? This thing that I'm claiming is linear. What that does to x is cross product with a fixed vector a. So with the understanding that c represents the act of crossing with A, I'm claiming that act is linear. In other words, the act of crossing with A plugged into the formula at the top of this page, that both sides of the equation will be equal. Okay, so you can confirm both of these using established known properties of dot product and cross product. It's just kind of a matter of writing it down and doing the algebra. Okay. One other thing. Let me point out. Also, anytime that I make a suggested exercise, hey, give this a try, right? It's always, I hope it will always be understood that if you get stuck, if you have trouble, you ask your friend, they don't know how to do it, I'm very happy to help you myself, right? Come to office hours, right? Totally happy to. In fact, if you come to office hours and ask such a question, there's probably a couple other people that are in the room that'll be like, oh, good, I was hoping someone would ask that, right? Totally fine. Happy to help. And again, reminder, don't forget about the help room. Don't forget about the other instructors, etc. Okay. Let's see, how are we doing on time here? Okay, that's okay. So, determinant. It would appear this suggests, right? After all, D, the formula for D involves a determinant. Kind of looks like this is saying determinant is linear. Now, very importantly, no, it is not saying determinant is linear. In fact, determinant is not linear. Here's a nice little exercise. Find a counterexample, right? Find an example where the linearity requirement would fail for determinant. Think of corresponding matrices and stuff. So determinant is absolutely not linear. But again, that's not what this says. What this says is that D is linear. D is what happens to X in this formula. What happens to X in this formula? Well, a bunch of stuff happens to X in this formula. In this formula, the very first thing that happens is I take this X and I stack a bunch of other vectors on top of it as rows to make a matrix. That's a bunch of stuff, right? And then, only after that, we subsequently then take a determinant. Right, so that's not to be conflated with determinant itself. Determinant itself is a function that applies to an entire matrix. X is not an entire matrix. Okay, so this D thing is linear, and it's inconvenient to demonstrate this algebraically, but nevertheless you might have seen some examples of this. You probably saw in your linear algebra classes, I feel morally certain you saw row reductions, right? When you do a row reduction, you may recall there's a neat observation that you can keep track of how determinant changes as you do row reductions. If you look at those properties of, how do you keep track of how determinant changes as you do a row reduction, they're all special cases of this statement. They're all invoking the linearity in one row at a time. Neat fact. So again, you might not want to actually prove this result, but you can kind of relate to it by making those observations back in your, Math218 or Math221 experience. Okay, moving along. Here's a really important fact. Theorem. Euclidean linear transformations. Quick pause. What do I mean by Euclidean? The domain and the target are both Euclidean space, Rn and Rm, just nothing, no abstract vector spaces of functions or something like that, just plain old Rn and Rm. Euclidean linear transformation can always be represented with a matrix like so. Really surprising fact. Because the merely knowing that a function is linear seems to leave open a lot of possibilities. And this is a very rigid structure right here. This idea that, a formula has to be exactly matrix times x. This is a very rigid formula. This would appear to have a lot of flexibility. It's a kind of a qualitative, anything that satisfies this property. Surprising that every one of the green is always one of the blue. So let me show you how to prove this. It is a very clever argument. I did not think of this on my own. Somebody showed me. The person who showed me, someone showed them. We've all been copying back through history for who knows how long. So here's the idea. First of all, I'm going to point out that if you have a vector represented by coordinates, you can rewrite that as a linear combination of standard basis vectors. And there's different points of view you can take on why this is true. Why is it that this vector is a linear combination of standard basis vectors? One take I'll give you for your consideration is this is kind of the definition of coordinates. Right? Y'all remember the idea of change of basis? Right? So coordinates with respect to a basis means how would I write the given vector as a linear combination of those vectors. Right? So when I say that x1 through xn are the coordinates, that's literally saying that those are the coefficients in this linear combination, assuming the standard basis. There's that. There's different ways to think about it. Okay, so that said, we're assuming linearity. Linearity means that when you have a linear combination on the inside, you can rewrite that with the linear combination on the outside. That's all that happened here. Right? So the mere knowing that this is linear allows me to write that down. All right, and here's where the magic happens. I'm going to make a kind of a seemingly arbitrary choice. It's going to come out of nowhere, seemingly for no reason. I'm going to choose, with no justification for the moment, to make the columns of my matrix, as indicated here, the images of the standard basis vectors. Again, pulling it out of thin air. Now, if you're doing math, you're perfectly free to make stuff up, but then you have to justify that what you've made up actually makes sense in some way, right? My claim that I'm trying to get to here, I'm trying to show that that T of x can be written as A times x. That matrix multiplication will reproduce this linear transformation. So I've got to figure out how to make AX come out of this. And so here we go. It's just a matter of doing the algebra at this point. Keeping in mind, we already had this, just kind of recopying from up here, right? Nothing happened there. That's just recopying. Notice if I then plug in, as per my choice, that the columns are the images of the standard basis vectors. A sub whatever is T of E sub whatever, like so. And then if I remind myself that a linear combination of the columns is a matrix vector product, then lo and behold, we get that thing that we wanted. And sure enough, when you have a linear transformation, T of x can always be computed as A times x, where this specifically is your matrix A. This is the magic formula that always works. If you want to represent a linear transformation as a matrix, here it is. The columns are the images of the standard basis vectors. Is that cool? Everybody happy? Look familiar, perhaps? I hope this might have been covered in Math219, but again, I think this is really, really important, and I feel like it deserves class time. Okay. All right, so really important fact. Let's see how we're doing on time. Yeah, okay, that's going to work out just fine. So last thing I'll show you. This one does get swept under the rug a lot. I think it's a big deal, though, and that is matrix multiplication. You can think of, in some sense, as corresponding to compositions of functions, specifically compositions of linear transformations. So let me expand on that. What do I mean by this? If you have a couple of linear transformations, each of which is represented by a matrix, right? So S is represented by a matrix A, T is represented by a matrix B. If you compose, let's see here, if you compose the two linear two linear transformations, so what comes out of T, you plug in to S, right? This is regular old composition. The output from T is the input to S. That composition will give you another linear transformation that will also be represented by a matrix, and the matrix will be the matrix product. So corresponds in the sense that when you compose linear transformations, the effective result is to multiply the corresponding matrices. So a really important fact. Again, I think it's undersold. In some classes, they just kind of subtly assume that this works. It is an important fact. This is not to be swept under the rug. In a lot of classes it is. In a lot of classes they just don't talk about it at all. And I would think it's a good idea for y'all to appreciate this as being an important, not obvious result, and not as just obvious or given. Okay, and I'll bet you we're out of time now. Oh, no, well, not quite. We got a minute and a half. But I tell you what, I'm pretty sure I'm going to owe you a minute and a half at a later date. So why don't we go ahead and call it a day. Good to see you. Nice to meet you. Welcome to Math219. See you on Friday.